Welcome guys. So it's another video today. We're going to be looking at moments, which is the chapter 4 on the A2 mechanics book. And moments, this is an overlap of physics as well for those of you who do A-level physics. So just before we move on, what I'd like you to do is pause the video and have a look at this prior knowledge check question. Alright guys, so this is the answer for 1A, B, answer to 2A, 2B, and 2C. Okay, so moments. So if we were looking to find a moment is a force acting on a body. Okay, so up to this point, you've been learning about forces pushing or pulling a particle in a particular direction. So if we look at this particle here, we have the weight, which is 7g going downward, and we have these two external force, one going horizontal 4 Newton, another one at an angle of 5 Newton. So if the particle does not turn around, it just moves in a direction based on the sum of the forces. So for moments, we replace the particle with a straight rod, and we often call this a lamina. So imagine the rod had a fixed pivot point. Okay, and if you had a force of 6 Newton acting on it, it will not, spin. It will just go vertically upward. But if you applied that 6 Newton further away from the center of gravity, let's say here, we would expect this to turn clockwise. If we do the same thing, a 6 Newton force, but we went further away, what do you think will happen to this rod? Since we are further away from the center, we have a greater distance, so this will turn faster and it will turn clockwise. So there's two factors I want to take in. One, the magnitude of forces would be, if you have a bigger force, it causes more turn. And secondly, the distance of the force for the pivot point. So the bigger the distance, it causes more turn. So these are two key points you should write down. So for example, the further you push a door from the hinge, the less effort is required. Why don't you guys experiment this at home? So you'll see closer you get to the hinge, the more force you need. The further away, you'll need less force. So what we say then is the moment of our point is equal to force times perpendicular distance. So this is the formula that we need. So if we applied a 5 Newton force here, and it's 3 meters away from the center of gravity, if we take moment about c, we'll do 5 times 3, and that'll give us 15 Newton meters. And now the reason it's measured in 15 Newton meters, because you're multiplying a force, which is in newtons, times by distance, which has to be in meters, so Newton meters, 15 Newton meters clockwise. And it's important that you always mention the direction. If it's not in equilibrium, then you should state the direction, whether it's going clockwise or anti-clockwise. So let's take this example. So we have the center, which is a F, and we go force of 4 Newton, and it's 2 meters away, perpendicular distance 2 meters away. So this force, if we were to carry on and it's going to be 2 meters away from F, it's going to start going anti-clockwise. So we simply just multiply 4 Newton by 2 meters, and that will give us 18 Newton meters anti-clockwise. Okay, so let's have a look at this one. So why don't you guys pause the video, draw the diagram, and see if you could label the perpendicular distance. So here obviously the 4 meters is not perpendicular distance, so we draw a right angle triangle to work out the perpendicular distance. 4 meters is the hypotenuse, and this is the opposite side. So the distance, perpendicular distance, will be just 4 sine 30. So if we multiply the force with 4 sine 30, 4 sine 30 is actually just 2. So 9 times 2, that'll be 18. So So we'll have 80 Newton meters going anti-clockwise. So sometimes you will have a number of moments acting on a single point. So if we take this example here, we need to calculate the sum of the moments acting about the point P. So we'll label all the forces here. So we'll go force 1, 2, and 3. For force 1, the perpendicular distance is 3 meters. Because you've got 1 meter, another 2 meters. So it's 3 meters times by 5 Newton meter. And the direction of this is just going to be clockwise. Because if this is a pivot here, P, this will move clockwise. For the same for force 2, the perpendicular distance 1 meters times by 4 Newton, and this time this is going to go anti-clockwise. And finally the force 3 will go 1 times 3, so it gives 3 Newton meters, and this is going to go anti-clockwise. So we go 1 clockwise and 2 anti-clockwise forces. So if we choose clockwise, for example, to be a positive direction, then we look at the net of all the forces. It will be 80 Newton meters in the positive clockwise direction. So that means as a net force, this will be going 8 Newton meters clockwise. Let's say you've taken anti-clockwise as your direction and you would have gone minus 8 Newton meters. So all you have to do is just say, if you go minus 8, you'll just say this is just 8 Newton meters clockwise. You just negate the idea. So let's look at another example here. So we've got the pivot P here, and we have two forces, 5 Newton, which is 4 meters away, and another 5 Newton, which is 2 meters away. So if we do the same thing, label these two forces 1 and 2. For force 1, it's just 5 times 2 meters, so it's 10 Newton meters, and that one is obviously going clockwise. For 2, it's 5 Newton meters, so 5 Newton times 4 meters, so we've got 20 Newton meters anti-clockwise. So we'll see the net, 20 Newton meters minus 10 Newton meters, we've got 10 Newton meters anti-clockwise. Okay, so this is slightly a difficult one because we've got forces coming at an angle. So it's no longer just horizontal or vertical. So all I need you to do is just pause the video and draw a nice big clear diagram. Now I'll usually say to students, use about a quarter of a page. The bigger the diagram, it's easier to label all the forces. So take your time and draw the diagram. So force, we'll call this force 1, 2, and 3. Now, before we do any calculation, we need to work out the perpendicular distance from point P. So this length here is 1 meter, another 3 meter, so that will be 4 meters, and we need to make a right angle here because it has to be perpendicular distance. So it will be 4 sine 80 because you got angle of 80 degrees here. So 20 sine 80 Newton meters, and that will go clockwise. And next one is just perpendicular distance already, so it's 6 times 3, so 18 Newton meters anti-clockwise. And finally the last one, the perpendicular distance here, so the hypotenuse is 3 and the angle of 40, so it'll be 3 sine 40, and that's anti-clockwise. So if we take clockwise to be positive and do a calculation, we get minus 6.01 Newton meter clockwise. So that means it's actually going 6.01 Newton meters anti-clockwise. So when a rigid body is in equilibrium, the resultant force in any direction is 0. The moment about any point on the object will also be summed to 0. So if we look at these two forces here, 10 Newton meters, and they're both 4 meters away. So if we take a moment about the point y, so maybe just 10 times 4 meters, so that's 40 Newton meters clockwise, and for the next one 10 Newton times 4 meters, and that's 40 Newton meters anti-clockwise. So as both moments are equal in both directions, the rod will not turn and hence it will be in equilibrium. So let's have a look at this one. So the other one looked quite obvious because you can see 40 Newton meters both ways. How about this one? Now, do you think this one will be in equilibrium or not? So pause the video and have a go at it and see if you think it will be in equilibrium or not. So if we take force 1, 3 times 2, that will give us 6 Newton meters clockwise, and force 2, 1 Newton times 6 meters, that will be 6 Newton meters anti-clockwise. So as you can see clearly, both directions, both moments are equal in opposite directions, so it will be in equilibrium. Okay, so let's have a look at this question here. We're told the diagram to the right shows a uniform rod of length 3 meters and a weight 20 Newton, resting horizontally on supports at A and C, where AC is 2 meters. The key thing to remember here is we're talking about uniform rod. So if it's uniform rod, that means the weight is in the center. Since this is a 3 meter rod, we know from A to 20 Newton meters, from A to the weight 20 Newton would be 1.5 meters that way. So which means this distance from there to there must be 0.5. So now from A we will see there's a normal reaction, because if you got pivot at A, that means there's a force that's pushing it up. So that's our support here, and we'll call that RA. And another support the rod is getting is from C. So we'll say that's the normal reaction RC. So we're told that this is in equilibrium. If it's in equilibrium, that means everything going up must equal to everything going down. So RA plus RC would equal to the weight, which is 20. So whenever you get a problem like this, first attempt you should do is always look at it vertically. Now vertically, obviously, it's equal to 0. So everything going up is equal to everything going down. So now what we could do, because we're asked to calculate the magnitude of the normal reaction of both of the supports, we need both R and C at some stage. So what I'm going to do is take moment about C. So I'll just pull you across here. If I take moment about C, I only have these two forces to work with. Why do you think we don't need to work with RC? So clearly RC from C, the perpendicular distance is 0, so we don't need to worry about this. And that's the whole point of taking moments about C. If you take moments about C, we don't need to worry about RC. If you take moments about A, we don't need to worry about RA. So now we've got two forces. So if I do the force 1, which is 2 times RA, so with 2 RA clockwise, and for force 2, be 0.5 times 20, and that is anti-clockwise. And we are told that this whole system is in equilibrium. So that means clockwise must equal anti-clockwise. So 2RA equal to 10, which means RA would equal to 5 Newton. So now you don't need to take any moments, just substitute that into the first equation. So RA, so that's 5 plus something gives you 20, so clearly RC is going to be 15 Newton. Okay, so let's have a look at this question here. Again, we're talking about a uniform beam, AB of mass 40 kg and length 5 meters, and rests horizontally on supports at C and D. And we're given the dimension AC is 1 meters and DB is 1 meters. And we're told this time a man of mass 80 kg stands on the beam at E, and the magnitude of the reaction at D is double the reaction at C. By modeling the beam as a rod and a man as particle, find the distance from A to E. So we're going to draw a nice big clear diagram and fill in all the forces, all the distance. So what we see here is then the length AC is 1 meters, BD is 1 meters, so the middle bit must be the rest 3 meters. And since it's a uniform beam, the weight is going to be in the center, 40 G, so we're going to be 1.5 meters from C to the weight, 1.5 here, and we've got a normal reaction at C and a normal reaction at D. Let's see what the next part of the information says. We are told the magnitude of normal reaction at D is double the reaction at C. So I could simply replace RD with 2 lots of RC, because that's given in the question. This is RD is twice RC. So all I have to do now is, well, firstly, I've still got the man, his weight. So if I put ATG here, and I'm putting this more closer to D than C. I'm putting the man more closer to D. Now, why do you think that is? The reason I put the man closer to D is because D is experiencing twice the normal reaction force at C, so it's having to support twice as much. So the chances that man is more closer to D. And think about it practically, if 2 people were supporting this person at C and a person at D, a person at D was pushing up twice as much, the more likely the load is more towards person D. So you guys have to think about like this, apply a bit more common sense. So now, same as before, this type of question, always start off with resolving it vertically first. So everything going up equal to everything going down. So RC plus 2RC, which is 3RC, equal to 40G add 80G, which is 120G. So if we divide both sides by 3, it will give us RC equal to 40G. So now we know RD is twice as RC, so RD will be 80G. So now that we've got 40G and 80G, we could start thinking about the distance to E. So to work out the distance from A to E, I'm just going to call the distance X for now, or you could just call it AE if you want. So it makes sense to take moment about A, because I need to work out from A where E is. So if I take moment about A, I've got these forces to think about. I've got 4 forces here. So same as before, you need to think about perpendicular distance times by the force. So for the first one, 1 times 40, and that is going anti-clockwise. Force 2, 2.5 times 40, that'll give us 100 G Newton meters clockwise. For 3, we don't know the distance, but we know the weight, so we'll just call it X times 80G, and that is obviously going clockwise too. And finally, 4 times 80G, so that'll give us 320G Newton meters anti-clockwise. So now, since this whole system is in equilibrium, we just have to do clockwise equal to anti-clockwise. So if we add up the anti-clockwise, 40G plus 320G equal to clockwise, which is 100G plus 80GX. We could group them together and then cancel out the G's, and then that will give us 360 equal to 100 plus 80x. And if we simply calculate this, the distance or the x value will be 3.25. So the man is standing 3.25 meters from A. Okay, so let's have a look at another question. Again, we're talking about uniform rod. And it says uniform rod PQ is hinged at point P and is held in equilibrium at angle 50 degrees to the horizontal by force of magnitude magnitude of F acting perpendicular to the rod at Q. Given that rod has a length of 3 meters and a mass of 8 kg, find the value of F. So again, we're going to draw a nice big clear diagram. So now we're told the force F acts on it, which is perpendicular, and then the weight of this uniform rod, so it's going to go halfway, 1.5 meters, and the weight always acts vertically downward, so we'll have 8G going downward. So what we need to do on this one, if we take moments about point P, we'll have 2 forces to work with, the weight and the perpendicular force of F. So here, if you look at the diagram, clearly we can see the perpendicular distance if we were to draw a right angle triangle, this would be the adjacent side of this triangle of angle 50 degrees. So it's going to be 1.5 cos 50, the perpendicular distance, times by 8g, and that is obviously going clockwise. And for force 2, which is just the F times 3, so that's going anti-clockwise. And since this is in equilibrium, we could do the equation. So we say 3F equal to 12g cos 50. And if we simply just work that out, it gives us F of 25.2 Newton.